In this problem, I have this unbalanced wheel, and this wheel has a weight of 50 pounds. It's rotating clockwise with an angular velocity of 8 radians per second, and it has this moment of 80 foot-pounds on it. So we put this moment on it, and we want to determine the reaction forces at this point P, this middle point right here. It's not a balanced wheel, so its center of mass is not directly in the center. Its center of mass is at this point G, and this point G is 0.5 feet away from the center of rotation. So, like always, we want to identify all our forces on our wheel, and we want to identify our accelerations. So, if we draw our free body diagram, we want to put our reaction forces, and because this is rotating in a circle, so G is on a circular path. If it makes a full rotation, it's on this circular path. We know G is going to have some tangential component of acceleration and some normal component of acceleration. So if I put my point G in, I know for accelerations, it's going to have this normal acceleration, and it's going to have this tangential acceleration. And it's moving in this direction. So I'm just going to use a coordinate system that sort of follows what's going on. I'm going to say that down is my positive tangential direction, and to the left is my positive normal direction. So this works well when I assume my assume my accelerations, because I'm assuming a positive normal acceleration and a positive tangential acceleration. And then we know it's really mass times acceleration, so it's 50 divided by gravity and 50 divided by gravity. So these are my accelerations. Let's go and put my forces on. If I want a reaction force, I want to assume a positive force in my tangential direction, so just call this PT, and I want to assume a positive force in my normal direction, and we'll call this P sub n. And I chose these directions again because this is what I said my positive notation was. I said my normal direction was positive to the left, my tangential direction was positive down, and my forces, when I don't know what they are, reflect that. If I'm wrong, it will just have a negative sign on it, and it tells me my force is actually going the other way. Okay, so what other forces? I have this moment. So this moment is going clockwise and is 80 foot-pounds. And I have my weight. And my weight is going to go right through my center of mass. So my weight is going to go right here, and it's 50 pounds. So now these are all my forces and accelerations that are on my system. I can use the sum of my forces in my normal direction is equal to a mass times an acceleration in my normal direction. The sum of the forces in my tangential direction are equal to a mass times an acceleration in my normal tangential direction. And the sum of my moments about some point is equal to the moment of inertia about that point. And I'll get into that one in a second. So let's sum our forces in the normal direction. So we have the sum of the forces in my normal direction equals my mass times my acceleration in my normal direction. And I guess I'll just substitute in right here that this is equal to mass times my angular velocity times my distance to the center of mass. So sum of my forces in my normal direction, I'm going to have this P sub n, which is equal to my mass, 50 over g, times my angular velocity, which is 8, squared times the distance to my center of mass from the fixed axis, and this is going to be 0.5. So if I perform this calculation, I'm going to get my normal force is equal to 49.6 pounds. And since it's positive, it means it's pointing in the direction I drew it on my free body diagram. So let's look at the forces in my tangential direction. If I do this, again, I'm going to substitute in another expression for my tangential acceleration. This is going to be equal to mass times my angular acceleration times the distance to my center of mass. So my tangential forces are this PT, and again, this is down is positive, and this one to the left was positive. So PT plus 50 is equal to 50 over g times my angular acceleration times the distance to my center of mass from my fixed axis, which is 0.5. Okay, so this is PT plus 50 is equal to 0.776 times alpha. That's fine. Two unknowns, one equation. I need to go look at another equation. And the equation I want to use is the sum of my moments equation. Now, normally, I use the sum of my moments about my center of mass is equal to the moment of inertia about my center of mass times the angular acceleration. And we could do this, but what if we take our moment of inertia about this point P right here? If we take this moment of inertia about point P, two of my unknowns are going to go away. And I'm only going to have this 50 pounds and this moment right here that I have to account for. So I won't need to figure out what this tangential reaction force is, because I'm taking a moment of a point it goes through. So if I do that, I just need to modify the moment of inertia. So the equation I'm using is the sum of the moments about this midpoint, this P, is equal to the moment of inertia of point P times the angular acceleration. So we just need to figure out what this moment of inertia about point P is. And that's where this piece of information comes in really handy. So this is telling us our radius of gyration. So with our radius of gyration, we can figure out our moment of inertia of our center of mass. And this is the formula m k squared. So our moment of inertia about our center of mass is going to be equal to 50 over g, so we get a mass, times this 0.6 squared, and this is equal to 0.559 slugs feet squared. Now, this is great, except it's the moment of inertia of this point G right here. I want the moment of inertia of this point P. So we can use the parallel axis theorem to get the moment of inertia of point P. So the parallel axis theorem is going to say that the moment of inertia about point P is equal to the moment of inertia about its center of mass plus the mass times the distance from the center of mass to point P squared. So I have my moment of inertia of the center of mass right here. This is 0.559. And now I'm just going to add in my mass, which is 50 over g, times this distance squared, and this distance is 0.5. And this is going to give me a moment of inertia of this point P, which is 0.947 slug feet squared. And again, I wanted to get this moment of inertia about point P, because then I can take my moments about point P, because this moments about point P, you need to use the moment of inertia about point P, not the center of mass. So when I do this, I'm going to have, this is going to be positive. I'm going to have 80, which is this moment right here, plus 50 times 0.5. It's a positive because it's going this arrowhead first. 0.5 is the perpendicular distance, is equal to this 0.947 alpha. And right here I can directly solve for alpha, and alpha is going to be equal to 110.8 radians per second squared. It's going that way. I can plug this alpha right here back into this equation, and I can solve for my my tangential force, and my tangential force is equal to 35.9 pounds, and it's positive, so it's going down.